Hello everyone. Today I'm going to talk about database. So, okay, see, yeah. My name is Ed. As just like Ivan mentioned, I'm the CTO and the co-founder of PingCap. PingCap is the company behind the project TiDB. So maybe if you want to find the new TiDB is a really popular open source NoSQL database. Uh, so and it is originally inspired by Google Spanner, but with MySQL compatible query layer. So yeah, it is very popular in the open source community. And this is my, so if you, okay, sure. Okay, so, yes, now is the remote control. Yeah, okay, yeah. Okay, today I want to talk about the distributed database. More specifically, we are talking about the distributed database with shared nothing architecture. And I understand that HTAP have become the buzzword. Many systems claims they are HTAP systems, but I think from the user's point of view, it is very useful. But I don't think right now the existing systems call themselves HTAP are good enough. And the other hand, the HTAP systems lacks a standard. There is no standard of what is a HTAP system. So today, I will talk about some challenges of building the HTAP system as a developer and a researcher of the database. Okay. So I think the first challenge is nowadays the database system, the ability to scale horizontally is a must. Also, by the way, I don't think AWS Aurora is a scale out system. I think the only way to scale out is use a shared nothing architecture. So the first of all, the modern database should be scaled out without pain. The second challenge of HTAP system is, the keyword of HTAP is hybrid. In fact, the biggest problem of hybrid is how to run both OLTP workload and OLAP workload at the same time. And also at that OLAP requests do not affect the performance of the OLTP side. So it is a big challenge how to run hybrid workload on the same system. Many existing systems solve this problem by separating data replicas of OLTP and OLAP. But another issue is how to synchronize the data in real time. For example, on the OLTP side, you always have a lot of days insert, but on the OLAP side, how to synchronize the modification of the data from the OLTP side. So in real time, it is a big problem here. And just like I mentioned about the data synchronization, so another challenge of the system is like the pattern of OLTP workload and the OLAP workload are totally different. For example, the OLTP workload, often it is a large number of concurrent random writes and random deletion and updates. But typically, the OLAP system are more welcome to the batch load or batch deletion. So the data synchronization in this process can easily become the bottleneck. For example, if you have a super huge OLTP system, if you want to synchronize the data to another data warehouse, like another OLAP database like Greenplum or something like Redshift, you may create a data pipeline like Kafka or Parser, any other data pipeline system. But the data pipeline system will easily become the bottleneck if you have a very heavy OLTP workload. So let's talk about how TiDB solve these problems. Because I'm the creator of TiDB, and the TiDB's goal is to solve these problems. So this is today's overview. I think today's the whole talk is roughly divided into two parts. The first part, I will introduce optimizations on Raft, because the whole system is built on top of Raft consensus algorithm and our multi-Raft architecture. The second part describes how we build the HTAP database built on based on the Raft architecture. And because of the time limit, I will not cover the SQL and the distributed computing in today's talk, but I think it is also a very interesting topic. Maybe next time. So today we are just going to focus on the storage, Raft, yeah, and architecture. Okay. So before introducing our optimizations on Raft, I want to talk about the overview architecture of TiDB, which is, TiDB is a typical shared nothing database where the entire system is highly layered. The overall system is a SQL above transactional key value system architecture. So it's a SQL above NoSQL, something like SQL above NoSQL. The SQL layer will translate the SQL statement and to the key value operations happens in the key value part. In this diagram, the gray part, the PD, is data storage. It stores the data distribution, metadata information of the whole system. And the TiKV is the distributed row-based key value storage engine. And it stores the actual data. The actual data is stored in the TiKV and the Flash. And TiFlash is another type of storage engine. It is a distributed columnar storage that it will handle the OLAP requests. So I will introduce TiFlash and the TiKV in the next few slides. So as I mentioned, we are not going to cover SQL layer today, so we are just focusing on these parts. Just like the normal key value database, TiKV supports the normal operations like get, put, delete, scan in the key value layer. But unlike the normal distributed key value database like Cassandra or HBase, TiKV also supports ACID transactions. aka the cross-row transactions. That means you can begin the transaction, put, get, delete, multiple keys, and then commit. TiDB will guarantee the ACID semantics for this transaction. Under the hood, it is nothing fancy, just like Google Spanner. We just use phrase commit protocol for the cross-row transaction. But also due to the time limit, I will not going to talk about the transaction detail in this talk. Okay. So as I mentioned earlier, TiDB is a multi-Raft system. And what is multi-Raft, right? Some of you may hear about the multi-Paxos, but unlike the relationship between multi-Paxos and Paxos, multi-Raft is pretty simple. Like if we consider this is the single Raft, and yeah, pretty simple. Multi-Raft is just a multiple Raft group within the same system. So when I mentioned about when I mentioned that TiDB is a multi-Raft system, I mean that as a distributed nothing database, the data is distributed across multiple Raft group in the system. Each Raft group in TiDB is not very large. In our it is 96 megabytes. So you can imagine that all of the data is distributed across many 96 megabytes data chunk in the system, and the data range is also the data range, aka the Raft group, is also the smallest unit of data movement. So yeah. Okay, next page. And there are a lot of challenges in building such a system. I think the first one is many people's Raft is very slow compared to multi-Paxos. Because Raft is a strong leader protocol, and according to the Raft original paper, Raft has a strict requirement for the order of applying the log. But I would say the well-optimized industrial Raft implementation, the performance will be very good, even compared to the well-optimized multi-Paxos. And I think there is no difference in performance compared to Paxos. And what's more, Raft is easier to implement. So I'm going to cover some optimizations we have proven effective in our database. So another challenge is about the multi-Raft architecture. Because the data is growing dynamically, we cannot use a static way of sharding the data. You cannot static sharding the data because, and also I think sharding algorithm, including consistency hash, is under the category of static sharding. And the TiDB use a completely different approach. I would say it's just like the cell division. The data range is dynamically split and merged, which is Raft group is dynamically split and merged and move across different storage networks. And the basic reason, how to rebalance and how to do the data movement effectively is also the big engineering challenge. So let's talk about Raft. Okay. Honestly, I don't want to go too much detail about the basic of Raft today. I'm assuming the listener have some basic understanding of the Paxos and the Raft. Okay, so I will not talk about the one. So, okay. The first problem is why do you think Raft is slow, right? The reason Raft is usually considered slower than multi-pixels is because I think multi-pixels, some people think any node in the multi-pixels group can write logs. And so there is no, restriction on choosing a leader. When the log is accepted by the majority, it is considered the log committed. But since any node can write logs, it also implied that you may have holes in the log sequence. Yeah, here is an example. Multiplexers appears to achieve the higher write throughput, but it is it is worth noting that in the consensus algorithm, the replication state machine RSM and the consensus algorithm are two different things, right? Why I mentioned that because once a log being committed doesn't mean it is safe to apply to the replication state machine, ISM. The committed is not equals to apply. But for Raft, once a log is committed by leader, that means the log can be safely applied to the state machine, but multi-pixels not. So in this example, let's take a look at the multi-pixels example. For the leader, the number 10, the log number 10 can be applied to the state machine because there is no hole behind this log. But for the acceptor one, the latest log you can apply to the state machine is 7. For the acceptor 3, it is 8. Even though the log 9, log 10, log 11, log 12 reach the quorum and committed, but you can read from the replication state machine. So even you have a greater write throughput, but it is not safe to read the data in the ISM. Okay. Right. The Paxos allows hosts in the logs. So if you want to, so that's why people consider the multi-Paxos is faster than Raft, but in the database scenarios, I think they are they are equals, right? So if you want to implement the well optimized Raft, I think the following engineering optimizations are essential, and they are not. I think these optimizations are all engineering optimizations. They are not in the original paper of Raft, but we have proven they are very effective. Yeah. So I will introduce them one by one. First, the first optimization is pipeline. It's called pipeline. So since we made sure for each request, it follows the sequence of prepare, append, replicate, and apply. And because the append and the replicate involve the I/O operation, that may take longer. So when we have multiple concurrent requests, we can execute, for example, we can execute the next prepare operation immediately after we finish the first one, make it a pipeline, right? It's very straightforward because all the operations are handled, one by one. So after finish the purpose of request 1, you can immediately begin to handle the proposed operation of request 2. Okay, this is pipeline. And the second optimization is also very easy to understand, as we can batch a bunch of concurrent write requests and merge them into single Raft request. That means we can trade a small increase in latency. We have to batch some requests for a large throughput, right? And also, the batch optimization will greatly reduce the number of RPC. It is effective optimization on the very high stress system. If you have a very heavy workload, the batch optimization will be very, very useful. Yeah, the third optimization we found on the leader road. The third optimization is we found that on the leader side, the append log and the replicate the log to the follower could be done in parallel, because both of these two operation, like append and the replicate, involve they are IO operations, and they can and if they can be done in parallel, that will reduce the latency. It's very short. Yeah. So, but this optimization can be done only in leader. It is not. It doesn't work on follower. But I'll explain why here, so you can think about it as a practice, and it is not very hard to understand. Yeah. Okay. The fourth optimization is parallel commit. I just mentioned for ISM, a replicate state machine. In the ISM like Raft, a log being committed doesn't mean you can apply it, but it will be better use of IO resource if you could out of order apply or out of order commit. So is it possible? I think the answer is yes, but the answer is yes, but you need some third-party information to ensure there are no dependencies during these logs. For example, if you know that two Raft logs are coming from different concurrent transaction in the application layer, and the content of the transactions do not have any intersect. So, and then these two logs can be applied out of order, even though they are in the same Raft group. So I think the key point is that the out of order apply needs some external information. Yeah. My friends at Alibaba have brought this idea to life in this paper. They call it parallel Raft. And the core idea is what I mentioned above about using the third-party application information to decide whether the logs can be applied in parallel. So as you can see, a database from the application layer, we can have many transactions in parallel, but most of the transaction in our case, they don't have any conflict. So in this case, we can apply the logs from different transaction in parallel in our Raft layer. Yeah. And we open source all of these we extract our Raft implementation to the separate project, and it is written in Rust. So if you want to use this, you can check out this repo, and this repo is separated, well optimized Raft implementation. You can use it in your systems. Okay. The second challenge: how to how to safely split and merge data. We call out multi-Raft architecture. Okay. So what I just mentioned, we are the multi-Raft system. I think multi-Raft is a way to split and merge the data range dynamically. And of course, we have to guarantee the split and merge process is should be safely split and merge. And we can logically sync all the key value pairs as the range from negative infinity to positive infinity with all the keys sorted by byte order, right? Negative infinity to positive infinity. It's a data range. So in the initial state, the whole system only have one data range, that is from the negative infinity to positive infinity. And then as the data is written into the system, the range divided like the cell into smaller ranges. In our case, with a threshold of 96 megabytes. And on the other hand, when the key value pairs in the logical range are removed, and the actual size of this data range is very small, we can merge the two small ranges to one range to save the metadata storage space. And in our case, the threshold is 20 megabytes. Yeah, and what I need to say is that the data range is a logical concept. In the physical, the data is physically stored within the RocksDB instance within in the TiDB nodes. Okay. So the challenge is that the replicas group is distributed over different nodes, right? In our case, by default, every piece of data have at least every piece of data have 3 replicas by default. So how do you ensure all the replicas are safely splitted? And there's actually a consistency issues here. So how can you make sure all the data range are splitted? So the simplest idea is using a two-phase commit protocol. So we can use a two-phase commit to make sure all the ranges, make sure all the data in different nodes are split successfully. But the problem of two-phase commit is in practice, it is very complicated to implement another two-phase commit under the Raft layer. We built our transaction implementation on top of Raft, but if our Raft in multi-Raft requires the two-phase commit, it is it's very complicated. So we found another more creative way to make it happen. We consider that the split command as a special Raft log, and when this log special split log is committed, it means that the majority have already received the split command, and when the peer apply this log, that means they can modify the local metadata to create multiple to split locally. Right, it's also very straightforward. We consider the split operation as a Raft log, right? Is that just like this? It looks like very simple, but we may have some, there is a abnormal situation. For example, let's say we have the split log as a special Raft log, but the log can be committed once the majority reach this log. But Raft allows some of the peers, if some of the network partition happens, in this case, for example, the S3 doesn't receive the log, and it's okay. It is also, for the majority, they successfully split into two data regions. The split operation can be successfully finished. After, for example, and then after n rounds of split, merge, data movement, if the network partition still here, and for example, in this cluster, we can add some new servers, and the data have already rebalanced. The original server 1 and server 2 doesn't have any, and then the network partition disappear, and the S3 will will very confused that it will reach out to S1 and S2, and it cannot find any information about the range 1. So how to make sure the metadata of the system is always correct? Introduce a very creative way to solve this problem. In our implementation, every Raft group has a epoch, aka it's a logical clock. This logical clock combines two versions together. One version is the configuration version. It is the original configuration version, and another version is split version. And every split operation occurs in this range that will increase the split version. So we can easily compare two ranges epoch to decide whether which range is the newest range using this algorithm. So the larger epoch always win. So we stop this problem by introducing epoch here. Okay, the third challenge is how to move data around without pain, because we are building a distributed database, and from the application layer, the scale out process is totally transparent. So how to make it happen? And in our case, we are just using the membership change protocol, and I think it is very nice that Raft introduced a membership change protocol. In our case, if we want to do the scale out or data movement, it is just two steps. The step one is we can add a new member to this Raft group on the new node, and the second step, once the new replica have successfully added to the Raft group, and then we can remove the old member from the the old group, right? It's very, very simple. I will use an example to for example, right now we have 3 nodes, and within this system we have 3 data range. Okay, and then we add a new node to the system, and the system find that, hey, there's a new nodes, and the nodes node 4 is almost empty, and the system decide to move some data from the range to the 4. So the first step is add a new member to the range 2's Raft group, and then the second step is remove the old member from the range 2, which in this case is replica in node 1. But there is a tricky moment. If you implemented the system like this, you will be faced to a very tricky problem. Is that let me see. At this moment, short period of time, for example, we add a new node to the system, and range 2 will have 4 replicas in this moment, when the range 2 in store 4 is synchronizing the data. But what if the network partition happens here? So in the Raft consensus algorithm is a current-based algorithm. When you have 4 peer, right, the current number is 3. So when the network partition happens here, and both of the left side and the right side cannot reach the current, that means the data in range 2 cannot be, will be unavailable for this time, right? Because both side is only 2 peer. So we introduce a new role to Raft algorithm. We call it non-voter follower. So for the non-voter, for example, according to its name, it will not vote to the existing Raft group. It only catch up the logs and apply the snapshot from the leader. And then once the log have already successfully catch up with the leader, and then it will become the voter. So in that example, the new peer on node 4 will be the non-voter first. So the number of the voter in the original Raft group is still 3. Yeah, so yeah, I know there is still a very short period of time we will have 4 copies, 4 peers in the range for the range 2 before the O is removed. But this operation also greatly reduced the risk of data unavailable, and it is the foundation of our HTAP architecture mentioned. I will talk about it in the next few slides. Okay. So that is some information about the system architecture and some optimization of our Raft. And next, we will see how we combine this together into a usable HTAP system. Okay. Before we get into the details of HTAP, let's take a look at the definition of HTAP. It is hybrid transactional analytical processing. That means you have to run both the transaction and the workload at the same time. So that means the OLAP workload is need to be handled well. So I think I would say for the OLAP system, that the columnar storage engine is a necessary option for the OLAP system, and that many optimization for the high performance analytics, it is very difficult to achieve on the role-based storage engine. For example, in this example, when we run such SQL query, select average age from a table, even if we need to, even if we only need a certain column of data, but on the row-based storage engine, we still have to scan the whole table out. But on the columnar storage, however, we only need to scan one column of data. It is very easy to understand, right? And what's more, it is more, and the columnar storage, it is more CPU friendly, and that will greatly improve the cache utilization, and also allows the vectorization processing, using some technology like SIMD technology for the vectorization. Yeah, so that will be greatly reduce the CPU overhead when you have some OLAP workload. But I think nowadays, if you want to build a HTAP system, a popular solution is that use the different database for different workload, and you can use MySQL or Oracle for the OLTP side, and using some systems like Hadoop or Redshift or any other analytical database for the historical data, and use the ETL process to move the data from the OLTP side to the OLAP side periodically. For example, every midnight you can pull out all the OLTP, all the changed data from the OLTP part, and the batch loaded to your Hadoop or another OLAP system, and then you can do the analytical workload on the OLAP side. But this process, I think, it's not good enough, right? I think today's, especially for this architecture, today's data processing is is totally different, and you maybe sometimes multiple data stores, but every data store have a totally different semantic, totally different syntax, even different query interface. So you have to write a lot of ETL process and the data adapters. It is very hard to maintain this process. And another big challenge is sometimes that will is very when if you want to add a new data source, is very hard, and it is also very painful to maintain multiple systems. For example, I'm an expert of database or MySQL, but I'm not an expert in maintaining some systems like Hadoop. I'm not expert maintaining the Cassandra or Greenplum, things like this. So, and another big problem is that the data pipeline, you want to synchronize the data from the OLTP part to the OLAP part. You need to deploy another components like data pipeline. the popular solution is using Kafka. But just like just like I mentioned, OLTP and OLAP are totally different workload. So once you have a lot of OLTP, a lot of changes in your OLTP cluster, and Kafka, will become the for the data synchronization. Because the OLAP part sometimes cannot handle the immediately update and deletion very effective, right? And another problem is that because the OLTP system and the OLAP system are totally separated in the old days. Most of the OLAP system doesn't support transaction. So the process of ETL usually, the transaction information. This problem will be very critical when you have some systems for the banking system or financial system. They are very rely on the transaction and consistency, even for the OLAP workload. So you have to find another OLAP system to that supports transaction. It is really hard to. It is not very. I don't think there is a lot of systems supports transaction for OLAP workload. So the first challenge is how I think we want to solve this data synchronization. So we have to find the way to, for the low cost data replication. And in TiDB, we found that the multi-Raft architecture I just mentioned is a great foundation, right? And we can let's TiDB inside TiDB, it is a multi-Raft, and data have already distributed into many small chunks and small data ranges, and every data range is a Raft group. So that means we can add a new replica to the existing to every Raft group, but the data format of this replica is columnar storage. So we extended. So remember, I just mentioned the non-voting member, right? We introduced another role based on the non-voting member. We call it Raft learner, and it will not be the voter forever. For the Raft learner, it only synchronizes the Raft log. So it will not become the leader or for the election, for the voting. So that means that will almost zero overhead to the OLTP workload, because it is only synchronized logs. And in this kind of replicas, the data is stored into the columnar storage format. So this is the is a diagram shows the idea. For example, right now we have on the OLTP part, in the TiDB part, we have 3 replicas, and then we can add a new replica to the existing system in TiFlash node. The TiFlash node will store the Raft replica in the columnar data format. So the architecture will be like this. Just like I said, the multi-Raft architecture can easily scale out transparently to the application layer. So we can, the TiFlash will also leverage the benefits from the multi-Raft architecture. that means on the OLAP part, the data synchronization can be also scaled out. Yeah, once you don't and within this architecture, the OLAP part can be also easily scale out. Yeah. So the benefits of using Raft Learner to replicate the logs is the first of all, this architecture inherited the TiDB's elastic scalability, right? It's very straightforward because all the data is just from the overview from the very high layer, how can I say that? It is still the multi-Raft architecture, but the only difference is that the TiFlash replica is a columnar replica. And what's more, the beautiful things happen here is that, the transaction information, like the MVCC version, the transaction key, the transaction, the information is already in the Raft log. So that means we can still keep the transaction isolation level in the OLAP part, which is the TiFlash part. And the whole TiDB architecture is a SQL above NoSQL architecture. So the SQL layer is separated from the storage part. So the SQL layer can directly redirect the OLAP query to the OLAP part, but still have the isolation level, right? But another big challenge is that many people may think how to support efficient in-place insert, delete, update, because in the OLTP part, the workload is always like you can update, you can insert randomly. But from the OLAP part, some people may think, oh, you are the columnar storage. Is that static storage engine? Right. So how to implement it writable, mutable columnar store without sacrificing the performance in read. So it is a big challenge here. Okay. To solve this problem, we introduce a new storage engine for TiFlash. It's a local storage engine. From the OLTP part, we just directly use RocksDB, but for TiFlash, we use a homemade engine. Is also very straightforward. We separate the data into many segments, just like TiDB, and every segment have two parts. One part is stable part, another part is delta parts. Delta parts stores the changes of this data, and periodically we will have a background process to merge the delta part to the stable part periodically. And in memory, we have in-memory B tree for to store all the for the data lookup. Yeah. So the basic idea is to we separated the data change and the stable data, and then if we want to read, we will merge the data from both sides. If the change happens in the delta space, we will use the value in the delta part. But if there's no change in the delta value space, we will directly retrieve the data from the stable part. Okay. And compares to the traditional multi-level LSM tree. In our case, the LSM tree is 7-layer. So every read you have to do the multi-level merging, and for the delta tree we only requires a 2-way merge. So that will greatly reduce the write and amplification. So that's why the performance is very good for the delta tree engine compared to the RocksDB. You know, RocksDB is a general purpose storage engine, but delta tree is only designed for the the database usage. So we can combine all these components together. That means we can successfully isolate the OLAP workload and the OLTP workload, but under the hood, the data from both sides is synchronization is synchronized via the Raft log. That means it is nearly real-time synchronization, and it can be scaled out well. So as I mentioned, the compute component of the are separated from the storage part. So the SQL part will redirect the SQL query. If you have a OLAP workload, the query will happen on the node. If it is a normal OLTP workload, it will still happen in the TiDB nodes. So it is a physical isolation. And what's more, this architecture can also, have some, leverage the benefit from both storage engine. Even you have a single, even for the single SQL query example, you have the query like this. We want to join 2 tables, and there is a condition here. It is a index lookup, and also on the other table is the table scan. For the for the table scan operation, it is better to be done in the columnar storage format. But for the index lookup, this operator it is more friendly to the OL to the row-based format. So we can leverage the query the data from both sides and aggregate for the we do the final aggregation in the computing part and generate the result. So this is a small benchmark running TPCH using TiDB with TiFlash compares to AWS Aurora. And it should be noted that these OLAP tests are being performed, and the system is also performing the normal OLTP writes and updates. So that means the OLTP part is the data is always changing, and then we running the OLAP workload in this system. So you can see the performance is very good. Yeah. Okay. In the end, I believe that yeah, this is the last page. Okay. In the end, I believe that the HTAP system is not an fantastic, unrealistic fantasy, but with a good design, it is possible to support 2 different workloads on the same scalable distributed system. So that will make the business application truly move from what happened yesterday to what's going on right now. Okay, thank you. This is my talk. Okay, yeah, if you interested, you can check out our open source project, and this is my email and Twitter account. Okay, thank you.
Thank you, Ed, for your great talk. It was very interesting. I have found it pretty much fascinating, the opportunity of the query optimizer to use the benefits of the different layouts of the same data. I think it's a great idea.
Yeah.
And yeah, so now we can move on to the questions part of our talk. And the first question I would like to ask you is the question about your multi-Raft optimization. And I'm wondering, how do you think, is it possible to implement in the multi-paxes the same kinds of optimization that you implemented in your multi-parallel Raft thing, such as the out-of-order commits that exploits the dependency in between the data items in the database, and also out-of-order acknowledgement, and etc. How do you think is it possible to do the same in the paxes? And also, do you know, or maybe you're aware of any papers that talk about that regarding Raft, or I'm sorry, regarding the paxes, and also maybe you know some implementations of such optimizations for the paxes?
Okay. Yeah. The answer is, I think this optimization about the parallel commit in Raft is also can be used on multi-paxels. Yeah, I think it is because the consensus algorithm is, is different from the replication state machine, right? The paxels is only the consensus algorithm. It is not, the state machine. So I think the applying for the logs is, this optimization can be also done in multi-paxels. But I haven't seen any system or papers using this approach. The problem is, it is a little bit, it is there will be more challenges in engineering part, because it's not very easy to implement it. But from the theoretically, in theory, it is, I think it will work, right? Yes.
Have you finished?
Okay. Yeah. I think it's
okay.
It will works on the paxels. Yeah.
Okay. The second question is how hard it was to debug your multi-Raft, your fresh multi-Raft implementation. Did you involve some specific techniques to test linearizability of your implementation, or I don't know, whatever?
Yeah, it's a great question. Because the distributed system testing in the distributed system is a very hard problem. So the first, we use some TLA plus to prove that the algorithm is correct, and from the using TLA plus. The second approach is we heavily rely on the chaos engineering. We build a chaos engineering platform to inject the failure to the distributed system. to speed up the process to reducing the bugs. We also open source our chaos engineering platform. The name of the chaos, just like search, but it is chaos mesh. It's also open source. I think the chaos engineering is a good approach for debugging the complicated system like this. Okay, we also, in the old days we using Jepsen test. Jepsen test is also very good platform for testing the transactional distributed system like this. But the problem of Jepsen test is it only works in small data set. For the large data set, the performance is not very well. So we create our own chaos engineering platform.
Which is called the chaos mesh, right?
Yeah, chaos mesh. CHAOSMESH. Yeah, chaos mesh.
Yeah, and it's already having stars.
Yeah. And I think another trick is, our testing platform is built on top of Kubernetes. So if you want to build a system like the chaos testing platform, the hard part is to you maintain the platform or maintain a lot of scripts. But when you use Kubernetes, that will the Kubernetes will handle a lot of complexity in deployment and for you. So yeah, I think Kubernetes is a you can do the chaos experiment in this. It's a good way. Yeah.
Okay. The next question is, where do you think to put more effort into regarding the optimization that is possible to do, besides what you mentioned? What areas you are interested in improving in?
Right now, yeah. For TiDB 5.0, my major target is increase the performance of our transaction system. The two-phase commit is that will generate a lot of latencies in the for writes or even for read. So thinking about introducing some optimizations to our transaction algorithm. For example, if I can, because our transaction model is using percolator model, it has a centralized timestamp oracle. So if we have the transaction will be, all the key value in the transaction will be happen in single node, I will not go to the two-phase commit. I can just do something like one PC that will greatly reduce the latency. And also maybe we can introduce some technology like hybrid logical clock that can reduce the latency across the retrieving the timestamp remotely. So next, from my point of view, in TiDB, I will go more into the transaction part. Yeah.
Okay. The next question I wanted to ask. Did I get right that originally you were inspired by the spanner architecture? And if it's yes, the question is how much you diverged from the original spanner architecture?
Cool. Yeah. I would the system is originally inspired by Spanner. You know, the Spanner is on top of the Collins's, the distributed file system. So, you know, I don't think Spanner have using some multi-Raft group architecture, like introducing some logical clock to make sure that the region and the data region is split safely, because the safety is guaranteed by the storage. But in our system, we don't have a distributed file system, so we have to do a lot of things to make sure the data is replicated safely. So this is the one big difference. Another difference is that we use a totally different transaction. We don't have a hardware clock, so we have to create a timestamp oracle, centralized timestamp oracle. So, and another big difference is that we speak MySQL protocol. Spanner is not compatible with the MySQL. And I think the TiFlash architecture is totally different compared to the Spanner, because the Spanner use row and column mixed data structure for the HTAP workload, but we separated architecture. So I think there's a lot of difference, but the Spanner the Spanner proved that such system is possible, and we can build a system like this. So that's yes, thank you, Spanner. Yeah.
Thank you very much. Thank you, Ed, for your talk. Thank you, Ivan, for having this Q&A session after the talk. And I remind you that we will have a Zoom webinar link just below here. Follow that one to ask more questions and to participate in Q&A with Ivan and Ed. Thank you, folks. I was really glad to see you here in this virtual room, and wish you good luck and bye-bye.
Thank you, Sarah. Bye-bye, everyone.
Thank you.
Bye.
Thank you.